All right, let's dive into a real-life detective story, but one that plays out in the world of sparkling, beautiful gemstones. We're going to uncover a gem's secret identity, a kind of hidden fingerprint that lets experts solve mysteries the rest of us could never see with just our eyes.
So, picture this. You're holding two gorgeous red stones. They look identical. Same cut, same size, they sparkle the same way. But one is an incredibly valuable ruby, and the other, a much more common garnet. How in the world do you tell them apart? That's the exact mystery we're going to solve today.
And trust me, the stakes are high. These two stones might look like twins, but they have totally different chemical identities and, of course, wildly different price tags. So just looking at them, that's not going to cut it. We need to find a deeper clue, something you can't see. So how do we crack this case? Well, it turns out that every single gemstone has a secret property, one that acts like its own unique fingerprint. And this is where our investigation really begins.
You see, it's not about the color or the cut, the stuff you can see. There's an invisible property that is constant for every single type of gem. And it's this hidden clue that lets a gemologist confidently say, aha, this one is the ruby, or nope, this one's the garnet.
So what is this secret fingerprint? Well, believe it or not, the clue is all about weight. But it's not as simple as just putting it on a scale. It's about how heavy a gem is for its size, a concept that scientists call density.
In the world of gemology, they call this specific gravity. And here's the really clever part. It's not just about a gem's own density. It compares that density to a universal standard that we all know, water. This gives us a simple number, a ratio, that makes it incredibly easy to compare any two materials.
If that sounds a little technical, don't worry. Just think about a bottle of salad dressing. You know how you shake it up, but after a minute it always separates? The oil, which is less dense, floats right on top of the heavier, more dense vinegar. Gems do the exact same thing in certain liquids.
And the baseline that makes this whole system work? It's just water. Water gets a specific gravity of exactly 1.0. So, if a gem has a specific gravity of, say, 3.0, it just means it's 3 times denser than the exact same volume of water. It's a really simple, elegant system.
Okay, so we know what the clue is, this unique density for every gem. But that brings up an even deeper question. Why? What's going on way down at the atomic level that gives each gemstone this unique atomic fingerprint?
It really just boils down to two things. First, its chemical recipe. What kind of atoms is the gem made of? And second, its structure. How tightly are all those atoms packed together? Let's check out a couple of amazing examples.
Okay, check this out. Diamond and graphite. Both of them are made of the exact same thing, pure carbon atoms. That's it. But in a diamond, those carbon atoms are packed together incredibly tightly, giving it a super high density of 3.5. In graphite, the atoms are in these loose, open sheets, so its density is only 2.2. Same ingredient, totally different packing, and a completely different density.
Now let's look at the other piece of the puzzle, the atoms themselves. Here we have aragonite and cerussite. They have the exact same crystal structure, the same packing, but aragonite is made with lighter calcium atoms, so its specific gravity is about 2.95. Cerussite, on the other hand, swaps out that calcium for much, much heavier lead atoms, and bam, its specific gravity skyrockets to 6.55. That's the atomic fingerprint right there. It's what atoms you use and how you pack them together.
All right, so we get the theory, we know what the clue is. So how do the investigators, the gemologists, actually find it? Well, they've got some pretty clever tools and tricks up their sleeves.
One of the classic methods is called the heavy liquid test. It's so simple, it's beautiful. You take a special liquid and you mix it so it has a very specific known density. Then you just drop your mystery gem in. If the gem sinks, you know it's denser than the liquid. If it floats, it's less dense. And if it just hangs out suspended right in the middle, bingo, you've got a perfect match. Its density is the same as the liquid.
Now, if you need to be super precise, gemologists can use something called a torsion balance. This is a bit more high-tech. You weigh the gem in the air like normal, and then you weigh it again while it's hanging in a liquid, usually water. The difference between those two weights lets you calculate its specific gravity with incredible accuracy.
But, just like in any good detective story, the investigation isn't always a straight line. Sometimes the evidence can be a little misleading. There are a few things that can mess with the measurements and throw you off the trail. Let's be honest, nature is rarely perfect. Tiny little cracks inside the stone, microscopic air bubbles, or bits of other minerals trapped inside can all throw off the final number because they have a different density. And sometimes, even something as simple as surface tension can make a really small stone float just a little, giving you a false reading.
And this is really where gemology becomes a forensic science. To get around these problems, you have to be meticulous. We're talking absolute cleanliness, being super careful with how you handle the stone, and even controlling the temperature of the room, because a tiny shift can change a liquid's density and ruin the whole test.
So after navigating all the challenges and using the right tools, we finally get to the final verdict. We're bringing our whole investigation to a close, and the importance of this one single hidden clue becomes crystal clear.
So yeah, there can be complications. It's not always a walk in the park. But even with all that, measuring specific gravity is still one of the most powerful and essential tests a gemologist has. It's reliable, it doesn't harm the stone, and it reveals a gem's true identity.
Which brings us right back to where we started. That ruby and that garnet that look identical. How do you tell them apart? You measure their specific gravity. The ruby will have a reading around 4.0, while the garnet is closer to 3.8. That one number, that atomic fingerprint, solves the case. It's the smoking gun once and for all.
It really makes you think, doesn't it? If one simple invisible property can tell you the true identity of something as complex as a gemstone, what other incredible clues and hidden details are hiding all around us, in plain sight, just waiting for us to find the right way to look?